Muy buenas tardes. Bueno, antes que nada, me voy a disculpar con ustedes, ya que una afección gripal me tiene un poco afónico, pero bueno, espero que lograr transmitir el mensaje. En nombre de la Fundación Global Democracia y Desarrollo, es un placer y un honor darles a todos ustedes la bienvenida a esta importantísima actividad sobre diseñando para la sustentabilidad y el crecimiento vertical. Esta actividad hemos querido, con esta actividad queremos abrirnos un nuevo formato de encuentros y dinámicas desde Funglode, siempre con el mismo objetivo de compartir con el público dominicano mejores prácticas, nuevas tendencias orientarnos hacia dónde se dirigen las tendencias en las principales áreas de interés nuestro. Funglode, el área del desarrollo es fundamental para nosotros, y el desarrollo sostenible, el cuidado al medio ambiente y todo lo que tiene que ver con la sostenibilidad, pues es un tema que siempre ha sido de prioridad en la agenda de Funglode. Y contar, con la presencia de los expositores del perfil con el cual contamos el día de hoy, creo que nos da la oportunidad, nos satisface mucho poder traer al escenario local agentes y protagonistas del escenario global en las áreas, por la cual nos sentimos muy complacidos de poder realizar esta actividad. No quiero, antes de concluir mis palabras de bienvenida, agradecer a Cronos Consulting, a Randy Guillén, a César Fernández, quien en nombre de Funglode han sido los responsables de poder incorporar y diseñar esta impresionante actividad a la cual auguramos mucho provecho y muchos éxitos. Muchas gracias por su presencia y su apoyo, y les deseamos una muy productiva tarde. Buenas.
Okay. Muchas gracias. Buenas tardes. I don't know much more Spanish, so sorry. I would like to say, for my colleague Wolfgang and myself, we're very pleased and very honored to have the opportunity to come here to your beautiful country, and very beautiful. We'd also like to thank Kronos and Funglode for the organizing the conference, and all the sponsors that I guess Cesar and Randy mentioned. So we would get started here. No, we don't have to look at that one. I just wanted to spend a few minutes, and then Wolfgang will come up, just explaining a little bit about who we are, the company. And we were founded in 1956, so we've been around for more than 50 years. Not myself personally, but company. We have a staff of about 650 people. We speak more than 40 languages, and we represent more than 35 countries. We have 26 offices around the world, 15 in the US and 11 outside of the US. And 1/3 of our design professionals are LEED accredited, and Wolfgang will get a little bit more into discussing that. We have sales over $100 million US, and the interesting thing about our company, I think, is that we not only do design work for new projects, but we do what we call forensic engineering and investigations of structures that have problems, anywhere from a crack in a slab to a building collapse. And we've done that for many years, since the inception of the company. And what it does for us really is it gives us an idea when we design something what can go wrong, because we investigate problems in other buildings. And we are one of the top structural engineering firms in the world. We do a number of different practices. We have 6 that we're showing here. Building structure, building skin, which is basically the facade of a building. Building performance, which is our investigation, forensic type work. Property loss consulting. We've been involved in a lot of the property loss damage in some of the recent earthquakes, Haiti, New Zealand, Chile, and so on. Construction support services, we do a lot of work actually with contractors, and we, for very complicated structures, we develop erection systems and that type of thing. And building sustainability, which Wolfgang is an expert in, and he'll be talking about that. Green buildings, et cetera, which I understand is very much of interest here in Santo Domingo and the country as a whole. And we serve a lot of different market sectors, commercial, education, et cetera. These are our office locations. We have to try to find one here in Dominican Republic, but we're working on it. Just very briefly, and I'm not going into all the detail of what we'll be talking about today, but Wolfgang will start with the sustainability concepts, and he's actually got 3 different parts to his talk. I'll talk about structural design of tall buildings, and then Wolfgang will again talk about thermal efficiency for facades, building envelopes, and then I'll talk a little bit about the World Trade Center. Those movies I saw in the beginning, I didn't realize we were going to show all those movies, but it brings back a lot of memories. And there'll be other things that we'll be talking about as well, but this is just kind of a general list. So with that, I will ask my colleague Wolfgang to join me. Thank you.
En lo que Wolfgang se pone su audífono, el área en la que estamos es un área de no fumar. Si usted siente la necesidad de fumar, le vamos a pedir que por favor lo haga fuera del salón. Los baños están inmediatamente cuando uno sale en una, digamos, edificación afuera, al frente y a la derecha. ¿Cómo vamos a manejar las preguntas y las respuestas? Si ustedes se fijan y miran a su mesa en este momento, hay unas libretas en blanco más pequeñas que dicen, haga su pregunta aquí. Durante la presentación del arquitecto y del ingeniero Cuoco, usted va a poner su nombre, si quiere hacer una pregunta, la empresa para la que trabaja, y va a tratar de escribir su pregunta en español. Hágala en español. Cuando estemos en una hora, digamos, dentro de la primera parte, van a pasar miembros del staff recogiendo esas preguntas. Y durante el break, cuando venga, va a haber una persona, el ingeniero César Fernández, va a tomar las preguntas, las que estén repetidas, él las va a echar a un lado, y entonces, antes de comenzar la segunda presentación, ellos se van a sentar aquí, el ingeniero Fernández va a leer la pregunta, y el arquitecto las va a contestar. Esa es la modalidad. Así que si pueden identificar dónde está su libreta, si no tiene una, quítele la mitad a la persona que está al lado, pero de que usted tenga una pregunta, la escribe entonces en ese papel. Tenemos refrigerios permanentes en ambas esquinas de este salón. Si usted tiene la necesidad de tomar algo, comer algo, o sea, simplemente póngase de pie, vaya a la mesa y sírvase. Vamos a pedir a las personas que estén paradas frente a esas mesas que, en la medida de lo posible, limpien un poco para que el espacio esté abierto para que las personas puedan accesar los coffee break. Ahora sí, vamos a darle la bienvenida al arquitecto Wolfgang Werner, con un fuerte aplauso.
Thank you. Thank you. So I put my phone here, but not to check my emails, only there's a timer. So I can try to keep track of the time here. Let me just switch the presentation here quickly. So as Daniel said, we're very excited to be here. It's my first time in the Dominican Republic, and I'm already sure that I will be coming back because I've already seen so much beauty in the country. So thank you very much again for having us. As it was mentioned earlier, my specialty is Well, first of all, I should say I'm an architect, not an engineer, so I'm surrounded by engineers in the office, but I'm one of the 50 or 60 architects that we have, and I'm very excited that finally building sustainability and green building is really taking off in the United States as well as in the world, in the larger world. And I have structured my talk here in 3 parts, and we're drilling down on the scale, let's say. I'm starting with the urban scale, and we're talking about sustainability on an urban level. Discussions about water efficiency, urban planning, transportation, and so on. And I know that some of those discussions and topics are very, very much relevant to the country of the Dominican Republic and the city of Santo Domingo in particular. And in my second part, so Daniel and myself, we will take turns just in order to keep it a little more interesting than talking about the same thing for 90 minutes in a row. On my second part, I'm going to be drilling down to the building level, and in my last part, we're going to look at the systems level, what I would call the systems level, the envelope system, the mechanical systems, and so on. So I hope this will be interesting to all of you. Let's get started. This is my divider slide. I have different divider images. So for the first part, here you see there's a satellite image of New York City, obviously one of the big metropolitan areas in the world, and both of our hometown and the location of our corporate headquarters. But let's take a step back and provide a quick background as to why sustainability and green building is important. You all know about the fundamental issue that we, for many decades, more than a century, have putting greenhouse gases in the atmosphere, which is a result of actually burning fossil fuels, oil, coal, natural gas, and that over time has led to a warming up of the planet as a whole, as illustrated by this photo, which is universally acknowledged by almost all scientists in that area, even though you hear from some politicians sometimes diverging views, particularly in the US. And that has led to certain phenomena that we're noticing. We have record heat waves in the summer. In the US, we just had the hottest first 6 months of the year ever. When we came down here, it was a nice 98 degrees or so. We have melting polar ice caps. We have melting permafrost, like here, let's say in Siberia or in Alaska, which can undermine the foundations of buildings because the solid ground is melting. And we have sort of an increasing number, it seems like, of extreme weather phenomena, wildfires, tornadoes, hurricanes, floods. To what extent all of that is tied to global climate change or not, I don't want to debate here, but it seems there's more and more of this extreme weather happening. Every year there are more and more records that are being set. Sometimes it's a cold record, but most of the time it's a new hot record. And how do buildings figure in all of that? Well, let's take a step back and think about what is the environmental impact of the built environment, of buildings. And we will realize in just a moment that it is rather significant. First of all, there is land use. Everywhere where there's a building, there cannot be undisturbed nature. So land use for buildings, for the supporting infrastructure, for roads, for the utilities. There's land use for resource extraction. And all of that goes along with the loss of habitat for, let's say, animals and plants. There's a disruption of water streams. There's a loss of farmland. So we have to balance our need for new land for construction against the need to also have natural resources, which also provide services to all of us, to the planet. There's resource use for construction. All of the stuff that gets into a building has to come from somewhere. There's iron ore, there are quarries, there's deforestation. All the building materials come from somewhere and from nature. So there's land use for that. There are associated impacts with that. There's a lot of energy that is being used for all of these activities. There's a lot of transportation. There's a lot of energy that is being used in the factories, in the steel mills, in the concrete mills, in the manufacturing plants, and all of that adds up and makes us a very power-hungry society. There's a lot of water used for a lot of industrial activities and manufacturing processes. Then once a building is built, there is an ongoing demand to use more resources, namely energy and water, just to run our buildings, to run our electricity, to run our mechanical systems, to keep the lights on, so to speak, to have water in our bathrooms and in our kitchens and in our factories and so on. There may be an additional demand for construction materials as we renovate our buildings, as we do additions, and so on and so forth. And then there is also an ongoing impact on the environment related to waste generation. There are different types. There's always construction waste. There's always things that go wrong during a construction project, and a lot of waste is being generated. Often there's first a demolition, and then you build a new building, so there's a lot of demolition debris that has to be discarded off somehow. And operating a building, be it an office building, be it a residential building, there is, well, waste, just ordinary household waste. Paper, food, whatever it is, all of this stuff has to go somewhere. Be it a landfill, be it an incinerator, or maybe to some extent you can recycle raw materials. And in summary, this is a slide from the USGBC, which is the United States Green Building Council, their main advocacy group for green building and sustainability. You can see some staggering numbers here in terms of the percentage in certain impact categories for which buildings, the built environment is responsible. 70% of electricity is being used in buildings, 40% of primary energy use, almost 40% of CO2 emissions. So this slide makes it very clear that if you believe, as I do, that we have to act on a global scale to slow the growth of greenhouse gas emissions into the atmosphere, you cannot solve that problem, you cannot solve that challenge if the building industry isn't front and center, if our industry, design, construction of buildings, isn't front and center trying to develop and implement solutions. When it comes to fundamental sustainability concepts for buildings, I'd like to take a step back and just reiterate, so to speak, the famous definition of sustainable development, which was defined by Grohal and Brundtland more than 20 years ago, who was a chair of a UN commission of, I think, long-term planning and sustainability. I don't remember the exact title right now, who said sustainable development is development that can meet the needs of the current generation, of our generation, that can meet our needs without compromising the ability of future generations to meet their needs, without, so to speak, undermining the ability of our children and grandchildren to also have a good life, to live on a planet where there are no planetary disasters. So simply put, that means our resource consumption and our overall habits have to be in a way that we don't use more than the planet in a way can replenish. So there's enough left for the future generations. And right now on a global scale, we're not doing that. Here's an interesting map that shows graphically what the environmental footprint of humanity is. And the darker it is, the bigger is the environmental footprint intensity in that location. So very, very densely populated areas and areas where people consume a lot, consumerist societies, just like the United States, for example, or societies that are not run very efficiently, they are dark. China, Europe, the United States. And if you translate that and look at it in a per capita way, here are all the countries in the world, and per person, who's using the most resources? Well, here on the left side, we have the top three, On number 2 is the United States, and this is not a good spot, this is not a good category to be a leader in my opinion. Flanked or bookended by the United Arab Emirates and Kuwait, 2 incredibly rich countries in the desert who have a lot of money to build new buildings, to have a lot of air conditioning, to have expensive cars and all of that, and who are incredibly rich. There's the United States, then followed by most of the industrialized nations like Europe, North America. Here's the Dominican Republic, just below the average. So that's a good space to be. You're not using more than the average in the world. You're not using more than you can afford to use. Trailed by a long tail of developing countries, let's say. So just imagine for a moment if everybody would go up to the American level, if everybody's aspiration to have a big house and a big car would become true overnight, we would have an instant environmental disaster on our hand. Not to speak that we wouldn't have the energy to power all of that. We just wouldn't have it. We don't have enough power plants. But this can't be our goal to get there. Our goal has to be to come down to an average that is sustainable over the long term. And how do we, as an industry, how do we come in? Let me just check the time here. Oh, no, it doesn't work. Anyway, how do we as engineers and architects come in? Well, first of all, we understand that it's all related. There are different, I think of it as different nested systems of environmental systems, and our sphere of influence goes up to the city level, and that's what we're here today to talk about. We influence from the room where a human being is in, to the site, to the neighborhood, to the city. That's where we can make a difference, and that's where a majority of the world's population lives right now. So what is a green building? A green building, simply put, is a building that tries to minimize its own negative environmental footprint. And sometimes people think, well, that's a lot of high-tech stuff on the building, photovoltaic cells. That's probably going to be very expensive. But I would argue both of the buildings you see here are green buildings. One is very old and in Scandinavia, has a green roof, and is smart how it reacts to its climate and to its environment in order to have a small footprint. The one on top is one we worked on as structural engineers, the master headquarters building. That's a very high-tech building that has all the bells and whistles, and it's also a very green building in the middle of the desert. But there's no one-size-fits-all answer to the question. That's my point here, to what is a green building. It can be low-tech, it can be high-tech, it can be a small building, it can be a big building. But what it always is, it's a smart building being put together by a smart team. Otherwise, you can't have a green building. And if you have a green building, there can be substantial reductions in those various impact categories we saw earlier, as illustrated here by another slide by the Green Building Council. And that's what we're trying to achieve as an industry. That's what my passion is. That's what Thorn Tomasetti as a company tries to get to. So one of the subjects we're here to talk about is the vertical growth and the urban density of urban environments. And this is a very interesting and opportune subject in my opinion. So let's have a look, let's have a little fun with it. Let's look at some statistics here first of all. So urbanization is increasing everywhere on the planet. These are some charts from the UN. Now more than half of the people in the world live in urban or suburban environments, and that trend is not going to reverse itself. Here are some slides, and I only want to point out the ones in the top left corner of urban versus rural population. So the Dominican Republic on the left here in the 1950s had an 80% rural population, 20% urban, and a total reversal happened over 60 years. The United States started out already with an urban advantage, but the gap has widened, and right now the ratio is literally the same as it is in many other cities throughout the world, countries rather. Here's an example, New York City, our hometown, 20 million people in the greater metropolitan area. New York City proper alone, 8 million, plus the surroundings, 20 million. Santo Domingo, beautiful city. We had a chance to see it a little bit yesterday. Greater metro area, 3.8 million, at least that's what Wikipedia was telling me. By far the largest city in the Caribbean. So it seems our collective future is going to look more and more like that around the globe. Mega cities like in Asia, there will be favelas and slums. There will be transportation impacts and associated problems. And I wanted to take a quick look at different physical manifestations of our built environment. So there is the very high density model, New York City, here in Manhattan. Think Tokyo, think Hong Kong, think Shanghai. Followed by still a high density kind of older city, not very high on average, not as high as New York on average, like beautiful Santo Domingo here. And then we have, most so in the United States and maybe in countries like Canada and Australia, suburbs. Actually, more people live in the suburbs in the United States than in the actual cities. And this is just a random photo in Atlanta, Georgia. Very monotonous neighborhood. The dependency on the car is built in. You have to have a car, otherwise you can't get anywhere. And so single-purpose commuter towns like this are using a lot of land in the United States, no doubt, and are sprawling. That's what we call urban sprawl, and are, in my opinion, something that we have to get away from this model. And beyond that lies a ring of what we could call ex-urban environments, like here in Texas. Even bigger houses, they all have a swimming pool here. They use even more land. They're farther away from the city. They have to commute farther. And what does it mean in terms of the environmental impact? Well, here's an interesting slide on the left side that shows you clearly that the urban, this is a chart of all the counties in the United States. And the urban ones are the blue ones, the dark blue ones, close to the bottom. And on the y-axis, the vertical axis, you have energy use per household. And you see the urban ones are by far more efficient than the suburban ones and the rural ones. And the same message is conveyed in this chart here on the right side, that a very dense city like New York City is on average a lot more energy efficient than big sprawling cities like Houston and Dallas in a very hot climate in the south of the United States. Here's another very interesting map that shows you on little 10 by 10 kilometer square. So each little pixel there is a square, 10 by 10 kilometers, of how much greenhouse gases are emitted in those little areas. So you see the major metropolitan areas, you see the highways where because of the traffic there's a lot more emission. And it seems like the East is a lot doing a lot worse than the West. But if you translate that graphic into per capita statistic, you see that the worst performing areas are actually the ones in very non-densely populated areas where people are very reliant on individual car traffic and probably live in bigger houses than in the cities. And if you drill in onto the city level, the same picture emerges here. Here's a slide that shows you what are the greenhouse gas emissions for automobile use by area on the right side and by household on the left side. So it's a total reversal of the image. If you're in the city, if you're a household in the city, you have to use your car a lot less. You have a much smaller impact than if you live around the city in the deep red area of car country. And the same is true for New York City here. The same is true for every city in the United States and in many other countries. So there are, even though sometimes people think about cities, oh, they have so many problems with pollution and environmental problems, there are substantial benefits, environmental benefits, tied to the fact that cities are denser, allow you to be less car dependent, allow you to have higher efficiency because buildings are built in more compact masses. So there are substantial footprint benefits that allow cities to be overall greener places than the suburbs and the places beyond. So how can we translate that academic knowledge into planning strategies for cities? So again, going back and looking at what has the automobile, let's talk about mobility for a moment here. The automobile, the rise of the automobile really started in the post-war years after the Second World War, and it has led not only to environmental problems, but to some extent to the destruction of our cities. You see, this is downtown Houston. At some point in the 70s probably, you wouldn't know it because it looks a lot like a big surface parking lot, and I can guarantee you that each one of those blocks once had a building there in the 1930s and 20s, and there was a bustling commercial downtown district that has disappeared because planners thought it's more important to provide parking spaces for cars than to provide buildings for people to live and to work on. Not to speak of course, the traffic congestion problems that come from the commuter-induced traffic around our big cities. So there are substantial problematic aspects related to our car culture, and any good planning will have to start, in my mind, any good urban planning, city planning, has to integrate an aspect of transit-oriented development. You need to have a local transportation network. I was very excited to read about the Santo Domingo metro here on the lower right side, and I understand from talking to some of the gentlemen we met that it has been a very big success. Here in the center, you see this is Bogota, Colombia, which had a very visionary mayor for a long time, and they increased the bus system on dedicated bus lanes by leaps and bounds. Quite a big success in really solving the traffic problems, the severe traffic problems that that city had. New York City obviously has a very, very large subway system and bus system, and without it, the city would collapse. It would not be possible to compensate for that with cars. So that's where we have to be headed. And beyond that, there are the aspects of walking, of bicycling, motorcycling maybe, which not only is healthy for you, you get exercise, it also increases the livability and the quality of life in our city. So Santo Domingo is certainly very much a walkable, enjoyable city, as opposed to the one that I showed you just, Houston, Texas in the 1970s. So in terms of integrated planning strategies, the goal has to be exactly that model. And I want to briefly tell you about a rating system, a certification system, and I'm going to talk about LEED a little bit more in a moment in my next part. The LEED for Neighborhood Development rating system. So this is a system that gives you a framework as urban planners to plan walkable, livable neighborhoods with a density and a massing and a physical layout that induces or that is conducive to high quality urban living. We're not going to look at the details of that system in the context of this presentation, but I would encourage everybody who is involved with urban planning to check it out. And I want to close this first part here with a note on existing buildings. So it's quite an obvious truism that there are many more buildings already there than we're building new every year. So if we want to make a difference, again, if we want to drive down the environmental impact, if we want to drive down greenhouse gas emissions, we absolutely have to focus on existing buildings. Otherwise, we will not be able to make a significant dent in the short term, or not even in the medium term. So we have to focus on existing buildings. Many of them are old. That doesn't mean they can't be turned around into highly efficient buildings. But many of them are probably very inefficiently run, have old, inefficient systems, and there's a great opportunity to turn them around. This is an aerial photograph of New York in the 1940s, And many, many of those buildings are still around 60 years later. There's the Empire State Building, there's the Chrysler Building. This is the building where Thomas Edison's office is in, the New York Life Building on Madison Square Park, built in 1928. Great building, and now an Energy Star certified building, meaning an efficient building. So we have to study the systems, we have to study the windows and the envelopes, and there are great things that can be done with existing buildings. And there is also a LEED rating system I want to point out here, the LEED for existing buildings and operations and maintenance rating system. If you see on the left side the number of LEED certification in recent years, the blue bars are new buildings. That has gone down because the economy went into a tailspin, basically. But the green bars, these are the existing buildings, so they have taken the lead in recent years in turning our overall built environment around to a more efficient model, and that's a very good development. And I believe with that, I'm at the end of my first part. Thank you.
Al arquitecto Wegner por esta primera parte tan interesante de desarrollo sostenible. Ahora vamos a continuar con el ingeniero Daniel Cuoco en la segunda parte de esta conferencia. Please, Dan.
Thank you. Okay, now let's see. Works. Amazing. When Wolfgang was up here, you might have lost him in the towers. Okay. You won't have the problem with me. I just wanted to start off, just as a comparison. You know, we talk about tall buildings. Just to, this isn't the most current slide, but it just gives you an idea of comparing buildings. For example, the Empire State Building in New York, the Twin Towers, which we'll talk about a little bit later, the Sears Tower in Chicago, and then all the way Taipei 101, and then of course the Burj Khalifa in Dubai, which originally was called the Burj Dubai, and for various reasons they changed the name, Burj Khalifa. And that building is 828 meters tall, and it is by far the tallest building in the world right now, way taller than anything else. These are now the tallest buildings under construction at the moment. And the interesting thing here, the only one which is sort of in the middle there, is in New York City, the Freedom Tower, or One World Trade Center, as we call it now. It's the only building on that chart of the 10 tallest under construction that's not in China or the Middle East. So all those other buildings are in China, the Middle East, and particularly China is very aggressive right now with tall buildings. These happen to be some of the buildings that my firm has designed. Starting at the right, the Federation Tower in Russia, Petronas Towers, Taipei 101, and they go on and on. The next, well, then we have the Shanghai Tower, which is the twisted one, and Ping'an Tower, which is actually starting construction. And the one on the very left and I will talk about this at the end, is the Kingdom Tower in Jeddah, Saudi Arabia. That building will be a little over 1,000 meters, 1 kilometer. And it's for real. It looks like it's actually going ahead. They're about to start construction. And Saudi Arabia has a lot of money, so I think they're gonna build it. A lot of these buildings you design and they just never get built. We have one in Chicago, for example, the Spire. We work with the architect Calatrava, and it's also a twisting building. And that building started construction. They spent maybe $100 million in the foundations, and it just stopped. The developer was an Irish developer, went bankrupt. So right now there's a big hole in the ground and about 35 big caissons that who knows when that job will go ahead. So you never know. Some of the factors, when you do tall building design, there are certain factors that really come into play that are more critical than when you're designing a regular building, you know, a shorter building. As far as the loadings go, the wind and the earthquake loads are obviously the most critical. You have a very tall building, it's like a flagpole, and you know, any lateral loads on it are going to cause it to want to fall over. So those are the major loads that we deal with on a tall building. And then you have to worry about not only making the building strong enough that it'll stand up, but you have to control the movement of the building. There's the sway of the building, so as the building is loaded laterally, it's gonna deflect, you know, everything has some flexibility. And it's interesting because years ago, that's the only criterion that we looked at when we designed a tall building. And we said, well, at the top of the building, it shouldn't sway more than 1/400th or 1/500th of the height of the building. So if it was 400 meter tall, you said, well, I don't want it to sway more than 1 meter in any direction, okay? We found out quite a few years ago that it's more than just the movement, it's the acceleration of the building. Because some buildings, if they're very stiff and they have a short period or of vibration, you can get a lot of acceleration in the building, even though it doesn't sway much, but it accelerates, and that's very uncomfortable. People, you don't want to have a cup of coffee and you have waves in your coffee, okay, during a windstorm. So it's very critical. So now we actually design for the drift of the building or the sway, but it's probably more important to design for acceleration. Damping of the building. Damping is like in your car, you have shock absorbers, and different materials have different damping properties. Steel, if you take a building and you move it and it's made of steel, it'll eventually come back like your shock absorber, okay? And that's a damping characteristic in simple terms. Concrete building, same thing. As it turns out, concrete actually has a higher damping capacity compared to steel. So as we'll see, a lot of the tall buildings that we've designed are actually concrete buildings instead of steel buildings. And interesting because when we were preparing from the seminar, somebody asked a question. They said, you know, somebody said one time that concrete buildings are not good, the tall buildings. Well, it's not true, okay, and you're going to see that from here. So buildings, they can be steel, they can be concrete. It's all a function of the construction technology in the particular area. Ductility is an important factor. If you have earthquakes, you typically will stress the buildings more than you ordinarily would under a wind, for example. You want the building to be able to be ductile and be able to yield and have some reserve strength, so it doesn't just, you have like a sudden fracture of something and you have a major problem. So that's what ductility is about. Creep and shrinkage, I think I have a next slide, we'll talk about that. That's pretty much a function of a concrete building. Creep occurs when you have in concrete, if you have a sustained load, a load that stays there, like even just the dead weight of a concrete building. You build a concrete building, and just the weight over time, it'll actually creep down. It'll shorten. Okay. And this is something that's very complex to predict it, but you know it's something that you have to be concerned about when you design a concrete building. Shrinkage is as the concrete cures, it shrinks, you lose moisture, and so that causes the concrete to shrink as well. Construction technology, as I said, you know, if you're building a very tall building, you have to make sure that wherever you're building it, they can build it. You don't want to design a building with super high strength concrete, and you'll never be able to get that concrete in the location that you're building it. So you have to be knowledgeable of what the construction techniques are in the area. They obviously have to be cost effective. You know, why build a tall building? They do have a high premium. There are various reasons people build tall buildings. If you have very expensive land, you know, or you want to, you know, draw people to a location, it's an icon. Those are all reasons. A lot of times it's just ego, you know. Somebody says, I want to have the tallest building in the world. So that's another reason. But it has to be cost effective. Well, in the last case, maybe it doesn't have to be cost effective if you have enough money. Elevators, another issue. In fact, this was, for a number of years, elevatoring was a controlling factor in how high a building could be. Why build a building 1 kilometer if you can't service it with an elevator? It's going to take you 3 hours to get up top of the building. So, but now there are, you know, techniques. There are double cabs. They use a lot of these high-rise buildings use a double-decker cab, so they serve 2 floors at the same time. They have sky lobbies, that type of thing. You go to a certain height, take other elevators up, and so on. And if you have a very tall building, you need a lot of elevators, and you brought them all down to the ground, you wouldn't have any room to walk around because there'd be so many elevators. So anyway, it's a concern. When we design tall buildings, we have a lot of different systems that we can look at. For the shorter buildings, we will typically, I'm not going to go through all of these, typically a frame building. And as you get taller, you introduce other factors. We start with the frames, and then if we get tall, maybe 40 stories and higher, we'll go to braced cores in the building. So that adds a lot of stiffness to the building. And there's different variations of that. Okay, then we have tube buildings, which are like the Sears Tower, which is actually kind of a bundled tube, but the World Trade Center, in a sense, was the old World Trade Center tube building. Actually, it's like an airplane fuselage. All the lateral strength is in the skin, all in the exterior. Okay, so when you have lateral loads on it, it acts like a tube. I'm going to spend a little more time on this one. I have one slide just to explain this, which is the braced core with these, we call them outrigger trusses. So you see it a couple of floors here, we have these trusses that come out. And the reason I'm going to just focus a little bit on that is because, as you'll see from some of these other very tall buildings that are designed, it's kind of a variation on that theme of an outrigger. It's a little more sophisticated, but it's the same idea. And the whole purpose of that is, if you look on the right, you see the solid line all the way to the right. If you didn't have these outrigger trusses in there, it's a flagpole, basically. It'll deflect under a lateral load, a wind load or earthquake, and it'll increase, not even in a straight line, it's going to increase in a curve, okay? When you have the outriggers in there, these trusses, what happens is, and the little picture on the bottom explains it's the one on the top. If you have this truss here, if you try to move it this way, it's actually going to be held back from this column. So it's going to actually pull on this one, and it's going to push on the other one. Okay, so you could see that here. So what happens is that those outriggers, every time you have an outrigger level, the building's trying to deflect, but the outrigger is actually pulling it back, and it's causing loads on the external column. So it's going to pull up on one, it's going to push down on the other, and it controls the deflection. So you see the comparison. Obviously, it's magnified, but it shows the difference. Solid line without the outriggers, and the other diagram with the outriggers. It really controls the deflection of the building. And as I said, you're going to see this kind of repeat itself in some of the other buildings that we have. This just shows this happens to be for comparing steel buildings. The gravity system, or we say gravity steel, that's for gravity loads, that's vertical loads. That's people, it's live loads, dead loads, it's all of us in this room here, okay, tables, everything. Gravity is the only thing affected as opposed to the wind loads, okay? So the lower line, total gravity steel, as the height of the building increases, that increases too. Now you say, well, each floor, every floor is the same. Why would it increase? Well, because the columns get bigger. You have a taller building, you're carrying that much more load on the column. So that rise, that gradual rise in the bottom, is essentially pretty much heavier columns to carry the extra floors. The red line is that, for example, on that other chart where I showed the different systems, the lateral systems, if you use one kind of on the left and you try to use it for a building that was a lot taller, instead of going to another system, it would be very inefficient. That's why we have all those different systems. So the red line is if you kind of said, well, I still want to use this, I don't care, it's another 20 stories, I want to use that. Well, it's not very efficient. And it'll be a lot more expensive. And if you get that building built, your client probably will never hire you again because it's going to be too much money. So by changing the system, the middle line there, the other blue one, shows when you change the system as you get taller, you can still be relatively efficient. Okay, so that's the idea with this one. The building drift, as I said, a lot of the criteria are based on the height of the building, and this just shows is what we call overall building drift, which is at the very top of that diagram. That's the overall building. And then the other criterion that we have is interstory drift. So not only do you want the building not to drift that much or sway that much, you want every story should be controlled as well, because otherwise you'll have problems with your skin on the building, the cladding. Okay, so this is something that really has to be coordinated with whatever the cladding is on the building, because as the building moves, you have to make sure that you have joints that can accommodate it, and so on. Vortex shedding is a very interesting phenomenon, and it really comes into play when you're designing very tall buildings and super tall buildings. And what I say is crosswind loading. Basically what happens is that if you have a shape, even take the one on the upper left, just a circular or almost circular shape, you have the wind blowing from left to right, okay, which obviously is going to cause the building to want to move in that direction. As the wind goes around the circle, it actually separates from the shape, and it causes the building to move in the perpendicular direction. The diagram just below it shows what happens. So you're blowing the wind from left to right, and the building not only is moving that way because that's the way the wind is blowing, but the building is also moving in the left to right, well, top to bottom in the picture, moving in the perpendicular direction. Very interesting. And if you have a building, this is almost like a vibration. And if your building has a certain frequency to it, you can have very high accelerations in the perpendicular direction. Okay, that's why, and I'm going to talk about wind tunnel testing, that's where we figure out all these things when we have these tall buildings. So it's an interesting phenomenon. It happens with all buildings. The triangles, by the way, is the worst shape you can have when you apply wind to the face there, and the vortex shedding is so bad that you really get a lot of movement in the perpendicular direction. Typically, and we call that crosswind loading. So you're loading in one direction, but it's moving crosswind. The crosswind loading is typically the most critical condition when you're designing a tall building, and especially super tall building. And we'll talk a little bit about vortex shedding a little later on and how the shape of the building has affected that. So as I said, we do a lot of wind tunnel tests in order to figure that out. Basically, these buildings, many of you know this, okay, but these buildings, you make a scale model. It's maybe 1/400th, 1/500th of the height of the building, and you put it in a chamber, and usually on the upper right, you can see in the back, there's a gigantic fan that blows, and the building is in the center of the turntable, and you need to model all the other existing buildings that are around it, because the wind flow is going to be affected by those other buildings, okay? And also, if you notice in the foreground, in the upper left, it looks like the Burj Khalifa, but in the upper left, there's those little blocks between the turntable and the fan, and what that does, we learned about that a lot of years ago, is that it's, and this is what's called the boundary layer wind tunnel. What that does is it actually replicates the wind in a more accurate way before it reaches the building. It shouldn't be very smooth because, you know, the earth isn't totally smooth. So anyway, that's the idea. It's on a turntable because in the lower right, you can see these models are instrumented. Sometimes there are hundreds and hundreds of pressure taps in the building. So you start the fan, start the wind, and you measure the pressures. And you take all these readings, they're all connected to the computer, take the readings, rotate the turntable 5 degrees or 10 degrees, and you do it again. So you get the wind pressures on the building from every direction, 360, okay, just by rotating that turntable. I talked a little bit about accelerations, and there are criteria. This happens to be U.S. practice, which is very similar to other practices around the world. And typically, there's exceptions, but typically, let's say we'll look at a 10-year wind, with wind that has a 10-year recurrence, in theory. And a milli-G is 1,000th of a G, or a gravity, okay? So 15, like for residential, 15 to 18 milli-Gs would be 0.015 to 0.018 Gs, okay? A lot of you know this, but you know, just look at the relative values. Residential, and when you're doing your testing, you don't want a residential building to have an acceleration, maximum acceleration, more than 15 to 18 milli-Gs. Hotel, 18 to 20, because, well, people are there, they don't live there, usually. So maybe they can tolerate a little bit more. Office building, you can tolerate even more, 20 to 25 milli-Gs. Because if it's really that bad, people are going to go home, okay? So they're not going to stick around. So we use a little more lax criteria for office buildings. And retail, we say it could be 25 or more, okay? Again, not as critical. The residential is the most critical, because that's where you live. And you don't want to wake up in the middle of the night because your building is accelerating too much. There actually is something called a motion simulator. It's located in Newfoundland, and it actually, you go in there, and it's actually set up kind of nice. You go in there, and it actually will accelerate to whatever you want, 10, 15, 20, 25 milli-Gs. And we did this actually on the Chicago Spire. We brought the owners to experience what acceleration would feel like when we were designing the Chicago Spire, in order to determine whether or not they wanted to use a damper in the building. And we'll talk a little bit about dampers, heavy weight on, swings back and forth at the top of the building to try to control the acceleration. So we said, okay, we predict the building is going to be, 20 millig's or 15 millig's. It's within the normal practice, but we want you to know exactly how it's going to behave. So we brought them up there, sat in the building, and they did it. It's interesting, but this device was actually built for maritime use. It was actually, they trained boat captains to dock in heavy seas, and this is what they used it for. But anyway, it's used now to show owners how much your building's going to move. Damping, I mentioned a little bit about damping. That directly reduces the acceleration. It's like your car, the shock absorber, okay? You hit a bump, and then it brings it back pretty quick, hopefully. Concrete, better than steel as far as damping goes. When you don't have enough damping in the materials themselves, then you have to go to some supplementary device like a tuned mass damper or some device that will help the building come back to where it started from. You have to be really careful about this because they do occupy a lot of space. They do cost money. You have to maintain them, inspect them, and so on. So it's a decision that needs to be made. Just as an example, you put these things in on the left. That actually is the one in Type A 101. It's at the top of the building, and it's a pendulum type. It's hung. I'll talk a little bit about more of this later, but basically these dampers are put, actually one on the right is also, and that's the red ball on the right, and what happens is the building sways in one direction, the weight will actually pull it back the other way. Creep and shrinkage is an interesting phenomenon. It's something that you really have to be careful about when you have a building, particularly if it's over 40 stories. If it's 10 stories or less, you don't really worry about that. But if it's something between 10 and 40, you have to think about it. If it's more than 40, particularly a very tall building, very, very important. And you could see, for example, on the left, it's particularly sensitive if you have, let's say, a concrete core in the building, like your elevator core, and you have steel columns around it, okay? Because steel doesn't creep, but concrete does. So what happens is the concrete will, over time, under its own weight or under the floor loads, will start to shrink a little bit, and the steel is going to stay up. So what happens? Your floor is going to look something like that. So what you do is you actually preset your upper floors at a higher elevation, okay? As shown on the left. Under construction, you build the floors actually out of level. And at the top out, it starts to come down a little bit, and then at occupancy, it's still going to be a little higher at the core. So it's still going to be, if you put a pencil on the floor, it's going to roll towards the window, okay? But what you do is you predict that after so many years, 1 year, 2 years, 5 years, 3 years, whatever, the floors will level out, okay? And there's really not much more you can do. And it's not only a factor when you have concrete and steel, but take, for example, on the picture on the left, instead of steel columns, let's say they're concrete columns. So you say, well, it's concrete, not a problem. Not true, because the core of the building has certain stresses on it, because your floor beams and everything gets supported by the core. So that's stressed at a certain level. Okay, the concrete columns, usually you don't want really big concrete columns, or any kind of columns, so you'll use a smaller column. It's going to have higher stresses on it, okay? So the concrete columns that have a higher stress have a higher sustained load on them, okay? they're going to creep more than the core. So you have the same type of thing going on. So you really, it's something you really have to be careful about. There are ways to predict it. Probably the best way to do it, and you'll see from, for example, Petronas Towers is a concrete building. We did tests in the laboratory based on the concrete mixes and everything over a year to actually try to get a better handle on how much creep we get over the years. Okay, this is kind of the same thing. Height-related issues, well, the first one is, you have to worry about differential column shortening. The construction sequence for the outriggers, remember those outriggers I talked about, okay? Very important to figure out when to make those connections, because if you make them right away, when you're building the building, if you're going up another 20, 30, 40 stories, what happens is you're going to be loading the building and you're going to start putting stresses in those trusses. You don't want them to take the vertical load. You want them there for the lateral load. So sometimes you wait till a certain point and you make the connections later on. So you don't build in stresses that you don't want. Very important. And actually the Petronas Towers, I have an example of that. You have to check the verticality as you're going up. Just imagine if you have a really tall building and you make a little angle at the bottom, well, you get to the top, it's going to be really big, okay? So you got to make sure you're vertical, and these things are laser measured and surveyed as you go up with the building. It starts to go a little bit that way, you kind of bring it back a little bit. And you have to think about the effects on cladding and so on with these buildings. These buildings tend to move quite a bit, so you have to make sure you take care of elevators, stairs, etc. Okay, one example here is One Liberty Place. This building actually was completed in 1987. It's the tallest building in Philadelphia. If that means anything. We always have, for all of our tall buildings, we have a description. It's the tallest building, east of the Hudson River or something like that. So there's always a little story with it. 61 stories. I understand you have a building right now that's in construction that's going to be 60, 70 stories. 288 meters high. Used a brace core and outriggers. And this was the framing. Now the outriggers, you don't see trusses. You see these big, on the right, see these big diagonals coming down instead of the trusses. And those diagonals actually, and you can see on the left, on this section of the building, those diagonals actually go through 4 floors of the building. They're actually in the space, okay? And somehow the interior, but it was a very efficient system. We were able to design this building and save the owner a lot of money by putting these outriggers in. So, we can save you a lot of money, but do you want these things sticking through your floor? And the interior designer figured out a way. They actually made it a design feature of the interiors, okay? So these things actually just go physically through the floor, but very efficient system. But you see the idea on the right? Those every outrigger brings that building back under a lateral load. Now the bracing in the core, I've been showing the chevron bracing on the right, okay? So you say, well, why use X bracing or chevron bracing? You can really use either one, it depends. If you're putting openings or doorways through, obviously the chevron is the way to go. If you have every floor, you have a repeated opening. There are other advantages to the X brace, and I won't go into them now, so it's not always an obvious decision. Here's the Petronas Towers in Kuala Lumpur. At the time, when it was built in 1998, it was the world's tallest building, or buildings, depending how you want to say it. 88 stories, 452 meters. It has steel floor framing in the building. So the floors use steel beams and decking and concrete fill. But the core of the building, the columns of the building, and the outriggers, I'll show you the outriggers, are all made of concrete. Tallest building, tallest concrete building. Before I get to the outrigger, the foundation system was interesting because they had very steeply sloping bedrock, and you have a really tall building, you want to try to get the foundation onto rock. Wasn't possible here, so they used what they call barrettes, and they're basically square piles, cast-in-place piles. And they actually transfer the load of the building to the soil by friction, side friction, because they're not bearing on the bottom. And there was some grouting going on to try to enhance that capacity. It was interesting because the piles on this building are almost a third of the height of the building. That's how deep they went. A typical floor plan, as I said, steel framing. You could see the red is the concrete core columns. The lower right just shows the beams around the perimeter of the circle there, because it acts as a frame, the exterior, the perimeter of the building. And rather than use, typically when you have a frame building like this, you would have very deep beams, we call them spandrel beams, around the perimeter. They'd be maybe 1.5, 2 meters high, and they would go from, say, the ceiling of one floor to under the window of the next floor. Well, they didn't want to do that. They wanted to, have more space that was unobstructed. So we use these what we call haunch beams. So they're not prismatic. They don't not the same depth all the way. Kind of thicker at the column, and then they get a little skinnier in the middle. So these were I think 1.5 or 2 meters deep. So they were very effective. Needed close coordination though with the architecture and the structure and the MAT systems. Here's the outriggers. There were concrete outriggers, okay, and the way that was done is at the mechanical room, at the ceiling and the mezzanine and the floor, we came out with these with horizontal beams from the core to the perimeter column, and you see those little vertical posts in there to strengthen it when these things are subjected to bending. You want to reduce that length from the core to the perimeter, so you put these little posts in. But the posts weren't put in right away, so they were put in afterwards, because what will happen again, as the concrete would creep and shrink, you don't want to build stresses into your outriggers. Okay, you want to save them for when you need them. Wind tunnel testing was done. Obviously, you have a building like this, you do wind tunnel testing. The first test was done without the blue buildings, because the blue buildings aren't there. So the first test was done with the towers alone, and that was the condition. However, you have to think about, in the future, if there are going to be adjacent buildings, they'll affect the wind flow. Okay, they could make it better, they could make it worse. So what was done here, there was a whole other series of tests done, wind tunnel tests, putting in all these other buildings that they thought at some point in the future might be there. So they did 2 sets of tests, and we designed to the worst condition. The sky bridge is a very interesting feature. It's almost like a project in itself to design this between these the 2 towers, and the owner insisted on that because they wanted a link between, so people can walk from one tower to the other. It was very useful in the movie Entrapment with Sean Connery and Catherine Zeta-Jones, if you remember that movie. And also it provides an alternate means of egress from one tower to the other. So they were able to eliminate one stair in the tower, because they said, well, you can go over to the other tower. And it was also a tremendous symbol. There's a big park beyond the first slide. I showed that with water and everything, and they wanted it like as a symbol, a gateway to the park. The way it was constructed, it was built on the ground, the central section of it, with the top part of the two legs was lifted, and that was 325 or 350 tons to lift. So it was put in place. The red legs on the bottom, the sloping legs, were actually tied back to the buildings initially. Okay, so you brought the centerpiece up. At the end of the centerpiece, those red squares, it was connected, it was welded into place. Okay, then the legs alongside the towers were swung underneath, and the final connection was made between the blue and the red leg by bolting it. And it was quite amazing because they had this figured out so precisely that they didn't even have to burn the holes or over-ream the holes or anything like that. Everything just fit, which was, you can't get that to work on a two-story job, you know, forget about this one, but it was quite amazing. And this one here I wanted to show because, number one, I personally worked on this job quite a bit, and number two, it shows an interesting construction technique. Building is located in Florida. It's a 40-story building. We completed this in 1981. At the time, it was the tallest building in the state of Florida. And the structure, it was a fast-track structure, and we worked very early on with the contractor on the job. It was Peverini Construction out of Connecticut, and tried to come up, the owner was General Electric Company, and they wanted to come up with a system that would build this building very quickly. And the system we came up with was somewhat of a hybrid system. So the core, on the right-hand side there, you see that dark area in the core, is concrete. The floor framing and the perimeter is steel. So this is an example of where you have to be really careful when the building is built. The concrete will shrink and the steel won't. But besides that, the core was constructed using a slip form method, as opposed to just, you know, forming it and pouring the concrete, taking the forms and whatever. And slip forming is typically used for silos. It's used for nuclear power plants to draft the towers and stuff like that. And essentially what it is, and on the left you see a diagram, and at the upper levels, basically the upper part is a work platform. And as you go below that, this thing is constantly moving, okay? The level below the top level, they're actually placing concrete. The vertical rebars are already in there from the floor below, okay? And they splice them as they go up. So you have rebars sticking up from the floor below. And as the form is rising, you're placing the concrete and you're putting in the horizontal bars, okay? Because you can't put them in ahead of time because the concrete has to go. So you're doing that as the thing is rising. And it moves, and there are jacks on the top. There's special pipes put in the core. There's jacks on top. It's basically lifted. So the slip form is lifted, and it's moving, and you're pouring concrete, you're placing rebar, and it's going at a rate of 40 centimeters per hour. So very slow. But, and it's like an extrusion process, okay? Like you get a tube of toothpaste and you extrude out of the tube. Well, this is just the opposite. The concrete is there and the tube is moving. So it's a very effective way to construct. So the concrete, it sets as you're going up, and then the lower levels, they have finishers there that are going to finish the concrete as it comes out. So, you know, even though the concrete is relatively young, it's still stable enough so that when the form leaves it, it's only a 1.5 meter form, 1.25 meter form, and it just keeps moving. So it's a very interesting process. One of the main reasons they decided to do this was that they said, okay, we can do the core and we can start building the steel at the same time. Okay, this is going to save us a lot of time. So you would think so. So on the right you see, well, in the middle you see the actual thing. On the right you see is that the buildings going up. It was interesting because we had found out that a lot of people were watching this core as it was going up, and people would pass by, they said, wow, that's a really small building, and it hardly has any windows. You know, they thought that was the building, but it was only the core. So now, you see the core is almost finished, and we're just starting the steel. And the problem was, because you had an active slip form going on, they didn't want to have people working around it. Okay, so we had to wait a certain period of time before they could go with the steel. But it was a very interesting system. And here it went up, and the cladding was put on. Kind of a nice building. No longer the tallest building in Florida. And I think, if we try to catch up a little time, I think I'll stop here, and then we'll pick up, try to get us a little back on track here. Okay, so thank you.